One major type of statistical inference is designed to compare two or more samples by proposing and testing something called a null hypothesis. This video will introduce some of the concepts necessary for choosing and setting up a statistical test, and the next video will describe how you interpret the results of a test, in particular one result called the p-value. So let's use a deliberately vague example for this purpose. We'll cover specific statistical tests over the next few weeks. So this vague example we use to illustrate the process, we'll just ask the question, is there a difference in grain size, let's say mean or median, doesn't really matter now, between sand from a river and sand from a beach? This is an example I've used in previous videos. So when choosing an appropriate statistical test, the first thing you got to determine is the type of data that you're working with. So there's two main types. Often you'll have what's called continuous data, where the variables can take any value. The range might be bounded, but the measurements can be any real number within that range. For example, temperature, or density, or calcium concentration are all examples of continuous data. Density is bounded, it can never be below 0, but it can take any positive value, 2 or 2.3 or 2.4172 or whatever. So there are tests that are designed to compare continuous variables between two or more groups, as well as tests designed to examine the relationship between two or more, I suppose, continuous variables. So we'll talk about the specific tests in upcoming weeks, but for now it is important just to understand what continuous data is. So the other main type of data is called count data. So these are counts of items in categories, like the number of quartz grains in an area of rock, the number of species that survived in extinction, and so forth. Because they're counts, they must be positive values and they must be integers or whole numbers. You can't have a fraction of a species or half a quartz grain. So this data often comes in the form of a contingency table, which lists the counts of items in the categories. And we will come back to this type of data in a couple weeks. So once you've determined the type of data, and especially if you're dealing with continuous data, you often need to know the number of samples and the number of variables in order to choose the appropriate test. So most commonly you'll have a single variable, one parameter, one thing that you've measured that you're comparing between your samples. And so this is called univariate. There are tests designed specifically to compare two samples. So for example, comparing pH, which is one variable, between two lakes, two samples, two groups. Or calcium concentration, also one variable between two samples of granite, or shell length, a single variable between two different species of clams. If there are more than two samples, if you have more than two groups that you've made measurements from, then you'll need to choose a different test. To be discussed later, in actuality, all these tests are particular cases of a more general method, but we're not going to get into that. So for example, you might have pH measured in 5 different lakes. pH is one variable, so it's univariate, but you have 5 samples, 5 different lakes. You might have calcium in 4 granites, shell length in 10 species. So basically the difference is whether you have just 2 samples or more than 2 samples. So less commonly, you might want to compare more than one measured parameter at the same time. Doesn't matter how many there are as long as there's more than one, and this is called multivariate data, so it means multiple variables, multiple things you've measured. Like before, there are different tests if you want to compare just 2 samples or more than 2 samples. So example might be that you want to compare both pH and temperature in 2 lakes. Or you want to compare all of the major chemical elements measured in 4 different samples of granite. So finally, you should determine whether your data are normally distributed or not. The previous video on standard error briefly introduced the normal distribution. But basically, the key thing to note is that, and you've also dealt with this when you have looked at mean and median, is if the distribution of the values of the measurements is symmetrical, sort of has a peak in the middle with tails of about equal size, and is unimodal, a single peak near the center, you can run something called a parametric test, which assumes and requires that your data are normally distributed. If your data are not normally distributed, and especially if the data are skewed, which means not symmetrical, the peak is not in the middle, as shown here, you should run a non-parametric test. And again, we will discuss specific examples of these sort of tests in future videos. So this type of statistics, this null hypothesis significance testing, is built around attempting to reject a null hypothesis. So the first step is to formulate that null hypothesis. It's often referred to as H0, this H sub 0. So a good null hypothesis is a statement that must have a single, unique outcome that can be tested. So in our example here, we want to rephrase the question into a hypothesis statement. So our question is there a difference in the grain size? But we want to make that into a statement that only has a single possible outcome that we can test and potentially reject. So the most common choice of a null hypothesis is that there is no difference between the groups. So for example, we can say grain size is equal in river and beach sand. That's a good null hypothesis because it has a unique outcome, that there's no difference, the difference is 0, and it can be tested. In theory, you could choose any unique outcome. You could say river sand grain size is exactly twice as large as beach sand grain size, but this no difference null hypothesis is traditional. A null hypothesis, for example, that river sand is bigger than beach sand, even if that's what you think is true, isn't a good null hypothesis because there are infinite number of ways in which river sand could be bigger. It could be twice as big, 3 times as big, 0.5 times as big. So it's not easy to test and reject. You want a null hypothesis that has only one outcome, and traditionally that outcome is that there is no difference. You can also explicitly state an alternative hypothesis. Normally your alternative hypothesis suggests that there is some difference between the two groups, in this example at least, but you can specifically test if one group's mean is greater than the other or less than the other. So this is an extremely important warning, however. You can't choose your alternative hypothesis based on the data. Just because you look at your measurements and see that river sand is bigger, that doesn't mean that you can choose the alternative hypothesis that river sand is bigger. So from the photo, it's fairly clear that's the case, but your alternative hypothesis must be based on prior expectation, independent of the data. You have to choose it without even knowing what your data is, basically. So basically, if you have any doubt at all, just use a difference as your alternative hypothesis, and it is the default in all the tests interpreted in R. So basically, your alternative hypothesis will pretty much always be that there is some difference. You don't know which direction or how big, but that's what you're testing for. So once you have your hypotheses, you can collect the data. You can perform your experiment, you can look at the existing data, or whatever. The data is the statistical sample, and it's hopefully representative. It's hopefully a random sample of this bigger population. As I mentioned earlier, in the geosciences, you often aren't able to run a controlled experiment. You're looking at things that happened a long time ago in many cases. So it's really important to consider whether your sample is really representative of the population. Are there any biases that could affect your sample? This will be very unique to whatever sort of data you're working with, and if you're collecting the data, then you will hopefully have a good idea of whether what you've collected is biased in some way or not. But that's the key thing, and we're not really going to deal with that. It'll be implicit in all of the future things we'll talk about in this class, that the sample is a good representation of the population. So now we've set up our test. The next video will cover what you do when you get your results. You can put it into R and get the data back and get the statistical test results back. But then the question is, what do they mean? How do you interpret the results of a statistical test? And so that's what we're going to talk about in the next video.